Every correction has a history, and sometimes that history, examined carefully enough, reveals that the correction was itself the mistake. In 1917, Albert Einstein inserted a term into his field equations of general relativity, a term he had not derived from any physical observation, any experimental result, or any theoretical necessity that his colleagues found compelling. He inserted it for a reason that seemed at the time entirely reasonable. The universe, as best anyone could determine, was static. It was not expanding, it was not contracting, it simply existed in a state of equilibrium, as it had always existed and presumably always would. His equations, without the additional term, predicted a universe that could not remain static, one that must either expand or contract under the influence of gravity. So he added a term that counteracted gravity on the larger scales, producing the static universe that observation seemed to demand. He called it the cosmological constant. He gave it the symbol lambda, and for more than a decade it sat in the equations as a kind of gravitational ballast, a mathematical counterweight that held the cosmos in place. Then in 1929, Edwin Hubble published measurements showing that distant galaxies were receding from us, and that the velocity of recession was proportional to distance. The universe was not static, it was expanding. The original motivation for the cosmological constant, the need to hold a static universe together, evaporated. Einstein, by most accounts, called the introduction of lambda his greatest blunder. He removed it from the equations. The physics community largely followed his lead, treating the cosmological constant as an embarrassing historical footnote, the kind of ad hoc adjustment that theorists introduce when they do not trust their own equations and then discard when reality corrects them. For 60 years, that was the consensus. Lambda was a mistake. A beautiful theory had been temporarily disfigured by an unnecessary term, and the correction had restored it to its proper form. But in 1998, two independent teams of astronomers studying the brightness of distant supernovae made a discovery that overturned the consensus completely. The universe was not merely expanding, it was accelerating. Something was pushing space apart, on the larger scales with a force that increased as the universe grew. That something now called dark energy constituted, according to the best subsequent measurements, approximately 68% of the total energy content of the universe. It was the dominant component of the cosmos, and it had been entirely invisible to physics until that moment. When cosmologists looked at the equations to understand what could produce such an effect, a uniform, space-filling energy that drove accelerating expansion, they found that the mathematics had been there all along. In Einstein's field equations, in the term he had discarded in lambda, the greatest blunder turned out to be the greatest prediction, and understanding why change is not just our account of Einstein's career, but our account of how physics works, what equations know, and what it means when a theoretical framework resists the assumptions we impose upon it. To understand what Einstein actually did in 1917 and what he inadvertently discovered, it is necessary to understand what general relativity is, not in its technical detail, but in its conceptual architecture. General relativity is a theory of gravity, but it is not a theory of gravity in the way that Newton's theory was a theory of gravity. Newton described gravity as a force, an invisible attraction between masses, acting instantaneously across any distance, pulling objects toward one another in proportion to their masses, and inversely in proportion to the square of the distance between them. It was an extraordinarily successful description. It explained the motion of planets, the trajectory of projectiles, the tides, and the shape of the solar system with extraordinary precision, but it left the mechanism of gravity entirely unexplained. How did the sun reach across 150 million kilometers of empty space and pull the Earth toward it? Newton himself acknowledged the problem. He declined to speculate about the mechanism. He described what gravity did with extraordinary precision, but he offered no account of how it did it. Einstein's theory replaced the concept of gravitational force with the concept of space-time curvature. In general relativity, gravity is not a force acting across space. It is the geometry of space itself, or more precisely, the geometry of four-dimensional space-time responding to the presence of mass and energy. Matter curves space-time. Curved space-time determines how matter moves. What we perceive as the gravitational pull of the Earth is the effect of the Earth's mass curving the space-time around it, so that the path of least resistance, the path that requires no force, curves toward the Earth's surface. Objects in free fall are not being pulled. They are following the straightest possible path through a curved space-time. This is a radical reconceptualization. Space and time are not a fixed neutral stage on which physical events play out. They are dynamic participants in physical reality, shaped by the matter and energy they contain, and in turn shaping the behavior of that matter and energy. The geometry of the universe is not given in advance. It evolves, it responds, it participates. Einstein's field equations describe this relationship quantitatively. They relate the curvature of spacetime, described by a mathematical object called the Einstein tensor, to the distribution of matter and energy, described by a mathematical object called the stress-energy tensor. The equations are not simple. They are a set of 10 coupled nonlinear partial differential equations, each relating a component of space-time curvature to a component of the matter-energy content. Solving them exactly is in most cases extraordinarily difficult, but their physical content is clear. Geometry and matter are coupled. Each determines the other. The universe is a single self-consistent system in which the distribution of matter shapes the geometry, and the geometry determines how matter moves. When Einstein applied these equations to the universe as a whole, when he treated the entire cosmos as a single physical system and asked what geometry it implied, he found that the equations did not permit a static solution. A universe filled with matter would, under the influence of gravity, collapse. The mutual gravitational attraction of all the matter in the universe would pull everything together. If the universe were not expanding, if it had no initial velocity of expansion to counteract the gravitational collapse, it would contract. There was no stable, static solution. This was a problem, because in 1917 the universe appeared to be static. The stars and the nearby nebulae showed no systematic pattern of motion. The cosmos appeared, to the observational standards of the time, to be in equilibrium. Einstein trusted the observations more than he trusted his equations. And so he modified the equations, adding a term, the cosmological constant, that represented a kind of uniform, space-filling energy with a specific property. It pushed outward, counteracting the inward pull of gravity on the larger scales. With the right value of lambda, a static universe became a solution to the modified equations. The modification was mathematically legitimate. The cosmological constant term satisfies all the requirements of general relativity. It is consistent with the symmetries of the theory, with the conservation laws the theory requires, with the mathematical structure of the equations. It is not an arbitrary addition. It is, in fact, the most general term that can be added to the left side of the field equations without violating the theoretical framework. Einstein did not insert it because it was physically motivated. He inserted it because it was mathematically permissible and observationally convenient. And then when the observational motivation disappeared, he removed it. But there is a problem. The problem is that removing lambda did not make it go away. It made it disappear from the equations on paper. But the physical question that lambda addressed, whether there exists a uniform space-filling energy component of the universe that exerts a negative pressure and drives the expansion of space, did not disappear with it. That question remained open, and the answer, as 1998 revealed, was yes. Such a component exists. It is real. It dominates the energy content of the universe, and its effect on the expansion of the universe is described to extraordinary precision by a cosmological constant in Einstein's field equations with a specific positive value. Einstein did not make an error in 1917. He made an error in 1929, or rather he drew an incorrect conclusion from a correct observation. The observation that the universe was expanding was correct. The conclusion that the cosmological constant was therefore unnecessary was not. The expansion of the universe eliminates the need for lambda to hold a static universe in place. It does not eliminate the possibility that lambda exists with a different value and plays a different physical role. Einstein conflated the specific motivation he had for introducing lambda, the desire for a static universe, with the physical existence of the term itself. When the motivation was removed, he assumed the term was removed with it. But motivation and physical reality are not the same thing. This distinction between the motivation for introducing a theoretical term and the physical reality of that term is one of the most important and least discussed issues in the philosophy of physics. Theoretical physics is full of cases where a term or concept was introduced for one reason, turned out to be physically real for a different reason, and the transition between the two generated enormous confusion. The history of the cosmological constant is perhaps the clearest example of this pattern, but it is not unique. and examining it carefully reveals something important about the relationship between mathematical structure and physical reality, about what equations know that their authors do not. When Einstein wrote down his field equations in 1915, he was not simply encoding the physical observations available to him. He was discovering through a process of mathematical reasoning constrained by physical principles a structure that described the relationship between geometry and matter. That structure was more general than any specific physical situation he was modeling. The equations described not just the solar system, not just the behavior of light near massive objects, not just the precession of Mercury's orbit. They describe the dynamics of space-time itself in any configuration, under any distribution of matter and energy, at any scale. The cosmological constant is part of that structure. It is not an addition to general relativity. It is a component of the most general version of general relativity, consistent with its own internal mathematical requirements. When Einstein introduced it, he was, without fully recognizing it, acknowledging that his theory in its most general form permitted a uniform energy of space. When he removed it, he was not simplifying the theory. He was restricting it, imposing an additional assumption that lambda equals 0, which the theory itself does not require, and which, as it turned out, physical reality does not satisfy. The equations knew about dark energy before the astronomers found it. They had encoded the possibility of a uniform, space-filling energy component from the moment Einstein wrote them down. The cosmological constant was not a mistake inserted into the theory. It was a feature of the theory that Einstein temporarily suppressed and that the universe eventually forced back into view. This is a remarkable fact about the relationship between mathematics and physical reality. It suggests that when a physical theory is sufficiently deep, when it is grounded in genuine structural features of reality rather than in phenomenological description of specific observations, its mathematical structure can contain physical truths that its author did not intend and did not recognize. The theory is, in some meaningful sense, smarter than the theorist. It encodes more about reality than any particular motivation for writing it down. This is not a mystical claim. It is a pattern that recurs throughout the history of physics. Paul Dirac's relativistic equation for the electron, written in 1928, contained solutions with negative energy that Dirac initially dismissed as unphysical. He eventually recognized them as the prediction of antimatter, a prediction confirmed experimentally 4 years later, before which no one had any reason to expect that antimatter existed. The equation nu, Maxwell's equations for electromagnetism, written in the 1860s, contained wave solutions that Maxwell recognized as light, unifying electricity, magnetism, and optics in a single theoretical framework, and implicitly predicting the entire electromagnetic spectrum, from radio waves to gamma rays, decades before most of it was detected. The equations, nu, general relativity, written in 1915, contained the possibility of gravitational waves, ripples in space-time geometry propagating at the speed of light, which Einstein himself doubted were physical and which were not directly detected until a century later. The equations nu, the cosmological constant, belongs in this sequence. It is not an anomaly in the history of physics. It is an instance of a pattern, deep mathematical structures encoding physical truths that exceed the intentions and the intuitions of their discoverers. Einstein introduced lambda for the wrong reason, discarded it for the wrong reason, and the universe restored it for the right reason. The equations, written correctly and interpreted fully, had been telling us about dark energy since 1917. But understanding what dark energy actually is, what physical reality the cosmological constant represents, requires going deeper than the historical narrative. Because the restoration of lambda in 1998 solved one problem and immediately created another. The problem it solved was explaining the accelerating expansion of the universe. The problem it created was explaining why the cosmological constant has the value it has, a value that is, by any theoretical reckoning, one of the most bizarre numbers in all of physics. Quantum field theory, the framework that describes matter and energy at the subatomic level, and which is the other great pillar of modern physics alongside general relativity, predicts that empty space is not empty. It is filled with quantum fields in their lowest energy states, what physicists call the vacuum. And the vacuum in quantum field theory has energy. The fields fluctuate, even in their ground state, producing a baseline energy density that permeates all of space. This vacuum energy is a physical prediction of the theory, not an assumption. It has measurable consequences. the Casimir effect, the Lamb shift in atomic energy levels that have been confirmed experimentally with high precision, the vacuum energy of quantum field theory is mathematically exactly the kind of uniform, space-filling energy that the cosmological constant represents in general relativity. They are the same physical concept approached from two different theoretical frameworks, and so the natural expectation is that they should match. The cosmological constant observed in cosmology should equal the vacuum energy predicted by quantum field theory. They do not match. They differ by a factor of approximately 10 to the power of 120. That is not a small discrepancy. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. The vacuum energy predicted by quantum field theory, if it contributed to the cosmological constant at its full calculated value, would produce an expansion of the universe so violent that no structure, no galaxies, no stars, no planets, no atoms could ever have formed. The universe would have been torn apart in the earliest moments of its existence, long before any complexity could emerge. The observed value of the cosmological constant is not zero. That would be one kind of answer. Suggesting some unknown mechanism cancels the vacuum energy exactly. It is a small positive number, small enough that the universe could form structure, that galaxies could coalesce, that stars could burn for billions of years, that planets could orbit them, that life could evolve on at least one of those planets and develop the capacity to measure the cosmological constant. But the observed value is not derivable from any current theory. It is a measured fact whose theoretical explanation remains entirely unknown. This is called the cosmological constant problem. It is widely regarded as the deepest unsolved problem in theoretical physics, and it sits precisely at the intersection of general relativity and quantum field theory, at the fault line between the two frameworks that physics has not yet succeeded in unifying. The cosmological constant is not just a historical curiosity or an astronomical measurement. It is a window into the deepest unresolved tension in the foundations of physics. Here is Section 2, continuing seamlessly from where Section 1 ended. And windows in physics are not merely passive openings. They are constraints. They eliminate possibilities. They force the theoretical imagination into specific channels by ruling out everything that cannot pass through them. The cosmological constant problem is a window of this kind. It does not merely tell us that something is unknown. It tells us with considerable precision what any adequate explanation must accomplish. It must explain why the vacuum energy of quantum field theory does not contribute to the cosmological constant at its full calculated value. It must explain why the observed value is not zero. And it must explain why the observed value is what it is, small enough for structure to form, large enough to drive the current acceleration of the universe, sitting in the extraordinarily narrow range that permits the existence of complexity. These three requirements are not independent. They are aspects of a single deep puzzle, and the puzzle has a shape. The shape is this. The cosmological constant appears to be fine-tuned, not in the loose impressionistic sense that word is sometimes used, but in the precise quantitative sense that its observed value occupies an extraordinarily small fraction of the range of values that quantum field theory considers natural. If you were to select a value for the cosmological constant at random from the distribution of values that the underlying physics suggests are plausible, the probability of selecting a value in the range consistent with a structured, complex universe is vanishingly small. By some calculations, it is smaller than 1 part in 10 to the power of 120. Fine-tuning of this magnitude demands explanation. In physics, when a quantity appears fine-tuned, when it has a value that seems to require extraordinary precision to produce the observed consequences, there are, broadly speaking, 3 kinds of response. The first is to find a deeper theory in which the fine-tuned value is not arbitrary but is derived from more fundamental principles. The second is to invoke a selection effect, to argue that the value appears fine-tuned because observers can only exist in regions of the universe or versions of the universe where the value falls within the range compatible with their existence. The third is to accept the fine-tuning as a brute fact and acknowledge that current theory cannot explain it. The third response is not satisfying, and physics does not typically rest with it for long. The first response, finding a deeper theory, is the goal of the research programs that seek to unify general relativity and quantum mechanics. String theory, loop quantum gravity, and related frameworks all aspire, among other things, to derive the value of the cosmological constant from more fundamental considerations, None has yet succeeded. The value of lambda remains, in every current theoretical framework, an input rather than an output, a parameter that must be measured rather than calculated. The second response, the selection effect argument, leads into territory that is among the most contested in contemporary physics. If the cosmological constant can take different values in different regions of a larger universe, a multiverse, in one of its many theoretical formulations, then the fact that we observe a value compatible with our existence is not surprising. It is inevitable. We could not observe any other value because no other value would permit us to exist. This is an application of what is called the anthropic principle, the observation that the conditions we observe must be compatible with the existence of observers, and that this compatibility is itself an explanatory constraint. The anthropic argument has provoked intense disagreement among physicists. Some regard it as a legitimate scientific inference, a recognition that selection effects must be accounted for in any complete cosmological theory, just as they must be accounted for in any other scientific context, where the sample is not random. Others regard it as a surrender, an abandonment of the physicist's ambition to derive the values of fundamental constants from first principles, replaced by a statistical argument that can never be tested in any ordinary sense. The debate remains unresolved, and it will not be resolved here, but its existence is itself significant. It reveals that the cosmological constant, Einstein's discarded term, has become the focal point of the deepest questions in contemporary cosmology and the philosophy of physics. Questions about the structure of reality at the largest scales, questions about the relationship between physical law and physical existence, questions about whether the universe we observe is the only universe, or one of an enormous ensemble. These are not questions that Einstein was asking in 1917. He was asking a much simpler question: how do I make the equations describe a static universe? But the term he introduced to answer that question has expanded over a century into a theoretical object of extraordinary depth and consequence. Lambda began as a mathematical convenience and became a physical measurement, and then a cosmological crisis, and then a window into the multiverse debate. Its trajectory through physics mirrors the trajectory of the universe it describes, starting small in a specific and limited context, and expanding relentlessly into territory that could not have been anticipated at the origin. You are living in a universe dominated by dark energy. That is not a poetic statement. It is a quantitative one. Approximately 68% of the total energy content of the observable universe is dark energy, the physical reality that the cosmological constant represents. The matter you are made of, the stars you see, the galaxies that populate the observable cosmos, all of this constitutes less than 5% of the universe's total energy. Dark matter, which interacts gravitationally but not electromagnetically, and whose nature remains unknown, constitutes approximately 27%. The visible, tangible, directly detectable content of the universe, everything that has ever been observed, measured, catalogued, or theorized about in the history of science, is a small minority component of what exists. The dominant component is the one Einstein introduced, discarded, and the universe reinstated. This ought to change how you think about the universe you inhabit. The standard account of cosmic history, the Big Bang, the formation of the first atoms, the coalescence of galaxies, the ignition of stars, the emergence of planets and life, is a story about the 5%. It is the story of what ordinary matter has done over 13.8 billion years of cosmic evolution. But that story has been unfolding inside a larger structure, inside a universe whose geometry, whose expansion rate, whose ultimate fate are all determined primarily by the 68%, by lambda, by the energy of empty space. And the fate that dark energy is steering the universe toward is one of the most austere conclusions in all of cosmology. The cosmological constant, if it remains constant, if it does not decay or evolve over time, which current observations suggest it does not, will drive the universe into an accelerated expansion that eventually becomes so rapid that all structures beyond our local gravitational neighborhood will recede from us faster than light can travel between us. Not because anything moves faster than light through space, but because space itself expands faster than light can cross it. Distant galaxies will redshift into invisibility. The observable universe will shrink, not because the universe contracts, but because the region causally accessible to any observer contracts as the expansion accelerates. In the very far future, on timescales that dwarf the current age of the universe by factors that make the comparison almost meaningless, stars will exhaust their fuel, black holes will form, and then over incomprehensibly long timescales evaporate through Hawking radiation. The universe will approach a state of maximum entropy, not the violent, compressed maximum of a big crunch, but the cold, diffuse, structureless maximum of a universe stretched thin by accelerating expansion. This is sometimes called the heat death of the universe. Though the term is misleading, it is not hot. It is the final state of a universe in which all useful energy gradients have been exhausted, all complex structures have dissolved, and the cosmological constant continues to drive an expansion into an increasingly empty and featureless void. This fate was written into the equations in 1917. Einstein did not know he was writing it. He thought he was writing a description of a static, eternal, essentially unchanging cosmos. But the equations describe something else entirely, a universe with a beginning, a middle, and an end, in which the energy of empty space would ultimately determine the character of the ending. The static universe he sought does not exist. The dynamic, expanding, accelerating, dark energy-dominated universe that the equations actually describe is the one we inhabit. Identity in the context of a dark energy-dominated universe acquires a particular character. The structures that constitute identity, the patterns of matter and energy organized into stars, planets, biospheres, minds, are local, temporary, and cosmologically marginal. They exist in the 5%. They are sustained by the energy gradients available in that 5%, and they will persist only as long as those gradients persist, which is a long time by human standards, but a brief interval by cosmological ones. The universe is not organized around the production of complexity. It is organized at the largest scales around the geometry that lambda imposes, an inexorable expansion into increasing emptiness. This is not pessimism. It is precision, the local complexity, the richness of physical and biological and cognitive structure that has emerged in the 5% is real. It is extraordinary. It represents a degree of organization and information processing that the universe has not achieved in any other configuration we know of. But it exists against a background that is indifferent to its existence, in a cosmos whose dominant energy component drives relentlessly toward a state in which such complexity cannot be sustained. You are, in this precise sense, a temporary structure in a universe whose primary physical character is expansion into void. The atoms in your body were forged in stars, the stars formed from gas that condensed under gravity. The gravity that drove that condensation operates in a space-time whose large-scale geometry is determined by a cosmological constant that Einstein introduced in 1917, discarded in 1929, and that the universe confirmed in 1998. The chain of physical causation that connects the energy of empty space to the existence of a mind capable of contemplating that energy is real, unbroken, and verifiable. You are a consequence of lambda, among other things. The dominant energy of the universe is part of the causal history that produced you. Free will, meaning, purpose. These are questions that the cosmological constant does not answer and does not pretend to answer. Physics is not in the business of providing meaning, but it is in the business of providing accurate descriptions of the context within which meaning, if it exists, must be located. And the description it provides is this: you are a complex information processing structure composed of the minority matter component of a universe dominated by the energy of empty space, existing during a cosmological epoch in which energy gradients are still sufficient to sustain such structures, in a universe whose long-term trajectory is toward a state in which no such structures will exist.